So this is the picture I would like you to have in mind. So you have some black box, right? So you have examples of inputs, let's say cats and dogs, and you want to classify them, right? So this is a very simple version of a machine learning problem, right? So this is a supervised classification. Basically, what you can think of it as some sort of curve fitting, right? So I give you a set of observations of an unknown function, right? So denote them by x and y, right? So x is the input, y is the output, right? We have n such observations. The function f is unknown, right? So this is our dog and cat classifier. And we want to predict its values at previously unseen points, right? So I give you a new example of a cat or a new example of a dog, and I want to produce the output of this function for an input that I have never seen before, right? So it sounds like an easy thing, but of course we need to understand a few things before we can proceed. So the first question is, how does this function look like, right? So the hypothesis class, right? So it can be something like this or something like this. The second question is how the sampling looks like, right? So how many samples we take. Is it millions or is it just a few thousands? Where to sample and so on. And then, of course, the question is how to find the fitting, right? So how to build such a function. So in broad categories, the answer to the first question, right, it has to do with the approximation, right? So what kind of class of functions are we proposing here? The second one is estimation, so this is mainly a statistical problem. And the last one is optimization, right? So typically we solve the fitting problem by solving some sort of optimization problem, okay? So let's define it from the very basics, okay? So we assume that our data, the input data, is high dimensional. So I denote it by this calligraphic X, but for practical purposes, assume that it's just d-dimensional Euclidean space, and d is very large, right? So hundreds or thousands or maybe even millions. The labels are in some label space that I denote by calligraphic Y, right? And again, depending on the type of the problem, it can be, for example, just the real numbers. So this is typical for regression problems. Can be just some set of classes, right? So this is typical for classification problems, or it could be something else, right? So it could be, for example, have the same structure as input, right? So structured prediction, segmentation problems. So for example, if I want to produce some physical properties of a molecule, right? So this is regression problem. If I want to tell that this image is a cat, this is classification. And if I want, for example, to segment the cat from the background, this is structured prediction, right? Segmentation. Now we'll assume that the data comes from this distribution, denoted by P of X and Y, right? So it's joint distribution of the inputs and the outputs. And what is important that it's unknown and impossible to model, right? We cannot model a 1,000-dimensional distribution, right? The samples are assumed to be drawn IID. So IID means that it's independent and identically distributed. So you can argue about whether this assumption is correct, and in most cases it's not, but this is one of these typical simplifications that people make in order for math to work. And often what you also know about the data, that the data forms some kind of low-dimensional structure. And again, there are many ways of describing it, but often it is the metaphor of a manifold is used. So this is often called the manifold assumption. So if you look at the distribution of cats, right, in the space of all the possible images, they will not be uniform distribution. So there will be some kind of low-dimensional structure, right? And this has been exploited for many years with, for example, nonlinear dimensionality reduction methods, right? So again, we'll not be talking about it, but it's often a characteristic of machine learning problems with real data. So this is true for images. This is also true for language. This is also true for proteins, right? So I would say that the only problems probably were that you can solve by machine learning methods will have some sort of degenerate, right, or low-dimensional solution space. So we also want to be able to measure the error, right? And this is quantified using what is called the loss function. So the loss function basically takes the output of your prediction, right, and right the label, right, that you're producing, and you compare it to the ground truth label. So typical, you see it in classification, right, or in regression. These would be the losses. And if I give you a function, right, that takes you from the input space to the output space, and I look at the loss, right? So I compare the ground truth label with the predicted label. I remind you that our data is sampled from some random distribution, so the loss is a random variable, right? So what I can do, I can take its expectation, right, on all the distribution of the data, right, and this way I give you a number, right, and this is called the population risk or the population error, right? So what will be the loss on all the distribution of my data? So I can write, so this is a double integral, right, over x and y, the inputs and the outputs. I can write an expectation that is conditioned on x, right, for every sample. What would be the loss if I take the expectation over y, right, and then I take the expectation over x, and again under some technical assumptions you can do it, and then you can ask the question what would be the best estimator for a given x, right? So this is called the base optimal estimator. So it minimizes the error point-wise, right? And of course this is only a hypothetical thing. You cannot really compute it in practice because it's defined through this distribution P, which is unknown in practice. And also the F star, right? So this optimal estimator, the way that it depends on x can be arbitrary, right? So it can be crazily behaved function, right? So it's not necessarily something that you want to deal with, right? And this is an illustration of how it looks like, right? So we have here just one-dimensional visualization of the input space and the output space, right? So this is our joint distribution P of x, y, right? So let's say that we have here cats and dogs, and this will be the conditional distribution, right, of the y given a given x, right? So for a given cat, this is how the labels will be distributed, and this is my function that I'm trying to estimate, right? So again, this optimal base estimator can be a completely crazy function, right? Because it's defined pointwise. Okay, so and here's an example, another example. So this is another point. Let's say this is the dog. So this is how this distribution might look like. So we clearly need something more manageable, right? And this is often called the hypothesis or a model class, right? So I want not just arbitrary functions, I want some kind of family of functions that are tractable, right? And typically we also want them to be parametric. So let's call it f sub theta, right? So for example, could be polynomials of certain degree, right? So the coefficients of polynomial will be these parameters. Or it could be neural networks of certain type, right? So maybe a two-layer perceptron, and the parameters would be the weights of the layers. And we can also judge the complexity of the model, right? Complexity, or sometimes it's called the capacity. I can measure it by associating some number, right? So let's call it gamma, with the parameter space, right? So I can, for example, measure it as the norm of the weights, or I can maybe measure it as the number of neurons in a neural network, or maybe I can use some, I don't know, Sobolev norm, right? So this is something that is that mathematicians like to use, right? So basically how fast, the coefficients decay, right? Or maybe it can be implicitly defined by the optimization algorithm, right? So if you solve a least squares problem with, for example, conjugate gradients, then we will always choose the smallest solution, right? So basically the algorithm, the optimization algorithm itself might act as some sort of regularizer, okay? So basically this will be what we will be dealing with, right? So now we are working with parametric functions. The problem is that we cannot really minimize the risk, right? The expectation over our distribution, because we don't know the distribution, right? So we need to approximate it. We need to replace it with what is called the empirical risk. So we replace the expectation of the loss with an average on the training set, right? So I sample my population of cat and dog images at certain number of finite number of samples, right? So this is our training set, right? So x, I, and j, and I define the empirical risk, right? So now it's called r hat, and basically I take the average of the loss instead of the expectation. Okay, so the difference between these and the actual expectation of the loss is called the generalization gap, right? And you can think of it as a random function that is an unbiased estimator of R, right? So something like this. So it will be distributed around R, right? But of course, it's random, right? So how big is its variance? It depends on n. So when n goes to infinity, it will become sharper, and then when n is infinity, it will be just a delta function, right? So it will be basically not a random variable anymore. So we can also ask the question is, what is the probability that the difference between, right, the absolute difference between R and R hat is greater than epsilon, right? And we can upper bound this probability, right? So basically it's the probability of having these tails. So typically these sort of results are known as probably approximately correct, right? So the approximate is this part, right? So the difference is greater than epsilon, and probably means that the probability that it is bigger than this epsilon is smaller than 1 minus delta, something like this, right? So again, there are multiple versions of these inequalities. So here in particular, it's the Hofding inequality. And again, you need to take into account that this result is for a particular f, not for the class of functions. So if you want to make statements about class of functions, you need more subtle analysis. So if you've heard of notions like VC dimension or Rademacher complexity, that's exactly the kind of analysis that is being done. I should also say that most of these bounds are irrelevant for deep neural networks because they are not tight. So the classical statistical learning theory doesn't necessarily have anything useful for at least for these kind of applications. So in supervised learning, we minimize the empirical risk, right, with respect to the parameters of the model class, right? So we basically think of f as a neural network and theta as the weights of the neural network. So we try to find the best weights that minimize the empirical risk, right? And we hope that this optimal estimator that we found generalizes well, right? So in other words, the difference between R and R of the optimal one, right, that we don't know, and the one that we found is small, okay? So just to visualize how it looks like, so this is my population loss, right? So this is the function R, and this is the ideal solution, right, f star, right? So the minimum of this function, right? So in practice, I have no idea how to solve this problem. I cannot even compute this function R, right? So instead I compute another function R hat that has a different minimum, and I hope to find the best empirical model, right? So you can obviously look at these two problems and say, why are we solving a different problem when we want to solve another problem, right? So it's like comparing apples to oranges. So I want to find an orange, but instead I'm offering you to find an apple, right? So the two things are not completely unrelated. And in fact, we can find this solution approximately, right? And we can actually bound the difference, right? So that would be the main derivation that I would like to show now, okay? What is also important that because we use optimization algorithms to find this optimal estimator, we not always are able to do it, right? And we can try to achieve a small training error, right? So being able to achieve it fundamentally depends on how rich our model is, right? So whether we can overfit the training set, right? So this is how often it is called. And in typical settings, deep neural networks have a lot of parameters. If the training set is small, you can overfit it, right? So we have multiple solutions. So you need to be able to choose the best solution out of these many possibilities. And this is what is achieved by regularization, right? So somehow you want to find the simplest solution possible. And again, there are many ways of doing it. So you can, for example, use it as a constraint or as a penalty, or maybe you can also think of interpolation. So I want exactly to fit my training set and then minimize some kind of regularity criterion, or as I mentioned, it can come implicitly from the optimization algorithm itself, okay? But let's look now at this error, right? So this is what, again, these are the apples and the oranges, right? So this is my optimal solution of a function that I cannot compute, right? And this is what I can compute in practice, okay? So let's see what is the relation between them, right? So I'm looking at this difference r minus r of f hat minus r of f star, right? So let me just add and subtract two things, right? And here allow me to cut the corners. So when we talk about minima, I should be writing infimum because minimum doesn't necessarily need to realize, right? But just let's write a minimum, right? So then we have a minimum and a minimizer, right? So we have also a point where this minimum is achieved, right? In practice, I should write infimum here, okay? And I hope you know the difference, right? But again, let's make things simple. Okay, so I didn't do anything here. So I subtracted the quantity and I added the quantity, right? So it's exactly the same expression. So what is written here is the best model in our class, right? So I remind you that f sub delta means all the functions, right, or all our parametric functions with capacity delta, right? So I basically restrict myself to a certain class of functions with certain capacity, right? So this is my best model in my class, right? Okay. So let's call it f theta star, right? And just write it here, okay? Now, what is written in this term, right? So this the green term, it's the approximation error, right? So how far is my best solution within my class from the optimal solution, right? So again, I'm comparing R to R, but this is the unachievable solution, right? F star that we said that we cannot compute, and this is something that I can compute in practice, okay? So again, I remind you, this is the picture. So this is the function R, right? So this is the ideal solution. This is my model class, right? F sub delta, and this is the best possible model that I can compute, right? Okay, and this is the approximation error, right? So how far, basically, how good my class is that I chose, right, with this complex capacity, how well it approximates the actual function that I'm looking for. Okay. Okay, so this is this term. Let's now look at these two gray terms, and again, let me write add and subtract two things, and they do not change anything, right? So I can always write add and subtract the same thing from an equation. So what is written here, right? So I wrote here r hat. So this is the optimization error, right? So I'm looking at the r hat of f hat minus r hat of f theta hat, right? And again, when we talk about optimization, I remind you that we do not guarantee that we find the global optimum, right? So this is my global optimum, right? Now of r hat of a different function of the empirical loss. Typical optimization looks like this, right? So this is what I can find, right? Because I do not necessarily find the global minimum. I can find something else, right? So this is the optimization error, right? So how far I am from the global minimum, right? So this is the optimization error. Now, if I look at this term, right? So what is r hat of f theta hat, right? So this is the minimum of r hat of f over all the basically bounded capacity by delta. So it's upper bounded, so it is smaller than the r hat of f theta star, right? Because f theta star is something that I was able to find, right? So I can replace the equality with inequality, so it becomes a bound. And what is written here, right? So I can look at this and then this. I can upper bound it by twice the supremum or the maximum, the difference between r hat of f theta minus r of f theta, right? So this is the estimation error. So this tells me how far the empirical risk is from the population risk, right? So basically how far is the apple from the orange, right? Because I'm minimizing a different function, right? So basically it looks at all the class of functions and looks at the difference between these two, right? So some kind of infinite norm, right? So the supremum norm of the difference between the two. So if I ignore for the second the optimization error, basically we have these two forces that contradict each other, right? So we have the estimation error and we have the approximation error. So what happens if I make my class smaller, right? So if I restrict my functions to be less expressive, right? So I restrict the capacity, so I call it f delta half, right? So for example, I have less neurons in my neural network, right? Or I make the weight decay smaller. So I can obviously increase the approximation error, right? But I decrease the estimation error. You see it? If I make the class bigger, it's the other way around, right? I decrease the approximation error because now I have more functions to choose from. But of course, the difference, right, between the r and r hat now needs to be taken on a bigger set of functions. Okay? So we often see it in the form of these trade-offs. So if I increase the model complexity, I improve the approximation, right? But I usually harm the estimation, right? And because our error is bounded by a combination of both, right? So I need to write this to look at the sum of them, right? And the generalization, right? What we are interested in behaves like this. So it decreases first with the model with the increase of the model capacity, and then it increases again, right? So the first phenomenon, we call it underfitting, right? When our model is too simple, right? Like here, right? I'm trying to fit a model, for example, a linear model to something that is non-linear, right? So this is underfitting. It's not complex enough, right? So it doesn't capture the complexity of the problem. The other phenomenon, right? So if I make my model too complex, this is called overfitting, right? So the model is just too many degrees of freedom, right? So I get some crazy excesses like here. Okay, so this is the classical picture, right? So this is called often a variance bias trade-off, right? And typically you are told that don't be too simple, you will underfit, don't be too complex, you will overfit. So somehow you need to be between the two, right? And that would be the right choice of the model. Now in deep learning, we often have way more parameters than the samples, right? So we can actually interpolate our data set, right? So the training loss can be 0. Right, so we are in a situation where we have these kind of interpolation thresholds. So when the model is sufficiently complex, I can actually my estimation error can be 0. Sorry, my approximation error can be 0. Right, so I can fit the training set. Right, and then what happens is that if I continue increasing the model complexity, right, I add more layers, for example, in my deep neural network, I will see that the error will go down again. And this is often called the double descent phenomenon, right? So you can think of it as a kind of modern version of the bias and variance trade-off. So it has been discovered or rediscovered. I think the most famous paper is by Michael Belkin, but it was probably known already years before that. Okay? So I hope I'm not telling anything new. So it was just a refresher on the basics of statistical ML. Let's now see what happens in high dimensions, okay? So basically the same thing, right? So this glorified curve fitting, but now we need to explicitly account for the fact that our input space is high dimensional, right? So we need to look at the underlying assumption of function regularity, right? So what does it mean that our function is well behaved, right? And how we define it, okay? So let's start with a very simple thing, right? So if I want to classify cats and dogs, so what would be the simplest thing is to say that here is a cat, right? And in my space of inputs, right? So let's say that I have two-dimensional images, right? X, Y, and X1 and X2, let's say. Everything that falls within certain radius around the cat will be considered a cat, right? So nearest neighbor classifier, right? So everything that falls within this ball of radius, let's say 1, right, or whatever epsilon, is a cat, right? And everything out is a dog, right? And if it's sufficiently small, again, if I assume some sort of regularity, right, that this function that tells me whether it's a cat or a dog is not completely crazily behaved, then it will probably make sense, right? So I can just take enough samples of cats, right, and just open a little ball around every cat, and everything that falls within this ball will be a cat, right? So how efficient is this, right? So let's say that we are looking at a unit square, right? So basically it's square that inscribes a circle of radius 1/2, right? So we have the in and the out, right? What's the ratio between the in and the out? So this is easy to quantify, right? So we compute the area of the circle, right, divided by the area of the unit square, which in this case is 1, right? So it's about 0.79, right? So most of it is cats, right? So most of it is green. What happens when we increase the dimension? So let's go to three-dimensional volume, right? So the volume of a sphere, right, a three-dimensional sphere in a unit cube will now be 0.52, right? So you see it's already about half cats and half non-cats. Right? What happens when we go to a high-dimensional sphere? So we can actually, there is a formula for the volume of a d-dimensional sphere, and I will spare it from you, right? You can find it online. So when the space is just 10-dimensional, it will be 2 over 1000, right? So 0.002, right? So it's mostly dogs and not cats, right? And you can see it here, right? So it decays exponentially fast, right? So this is exactly the curse of dimensionality, right? So basically this nearest neighbor classifier, the volume that is contained around each sample will become negligibly small when the dimensionality grows, right? And this is just 10 dimensions. Imagine this in 1,000 dimensions or in 1,000,000 dimensions, right? And the term curse of dimensionality actually goes to Richard Bellman, so the inventor of dynamic programming. So he was talking about the problem of dimensionality in physical problems. So everything works if you're in 1D or in 2D or maybe in 3D, but try to go to high dimensionality and bad luck, right? So in our case, the curse of dimensionality, right, because we are talking about machine learning that has these three sources of error. So we have approximation, we have estimation, and we have optimization. We'll need to look at how the curse of dimensionality manifests itself in all of the three, right? And we'll start with the curse in estimation, okay? So how do we learn multidimensional functions, okay? And so here we're talking about hypothesis classes, right? So we talked about regularity and I mentioned Lipschitz functions. So what are Lipschitz functions? A function, we say that function f is Lipschitz or beta Lipschitz if basically it doesn't change the distance by more than beta, right? So if I have 2 points x and x prime, they will be, and they're at certain distance, right? So that's measured by the norm, x minus x prime, it will not be expanded more by the factor of beta by the function f, right? So it doesn't blow up or compress things too much, right? So basically beta is called the Lipschitz constant, right? And it's a strong form of uniform continuity, right? So it's a global property unlike continuity, which is a local property. And again, if you're interested in the mathematical definitions, so that's the difference between continuity and uniform continuity, right? So basically this is a well-behaved class of functions, right? So continuous, right? So special type of continuity. Now let's try to answer the question, how many samples n do we need to approximate a d-dimensional Lipschitz function with accuracy epsilon, right? So here is what we do. We can construct a counterexample. So I build a one Lipschitz function, right? So how do I build it? So I take a unit hypercube, d-dimensional hypercube, right? So it's basically a unit cube in each dimension, and in the corners of this cube I place Gaussian blobs, right? So each of them is a one Lipschitz function, so their sum is also a Lipschitz function, right? And the Gaussian blobs comes with plus or minus sign, right? So it can be either minus or plus blob, right? So something like this, right? So you see this is an example of two-dimensional blobs, okay? Now, I am asking the question, how many samples do I need to take in order to approximate it with error epsilon? And the answer here, I will not go into the details of the proof, but you can always show it, right? So basically it is combinatorial, right? Because I can change the sign arbitrarily. You need a sample in each of the corners, right? Or somewhere nearby in order to get correctly the signs of these blobs, right? Otherwise you incur a big error. So basically here, the conclusion is that here's an example of a Lipschitz continuous function where the number of samples depends exponentially on the dimension, right? So even this simple problem is dimensionality cursed, right? So classical notion of regularity is cursed in estimation. Okay, so let's talk about the curse in approximation, right? So we talked about perceptrons, right? And we talked about perceptrons with 2 layers, right? So this is how it looks like, right? So we had this property of universal approximation, right? So we have this result that goes back to the 80s, Seibenko and Kornik. There are a few versions of it, right? But basically the idea is that this set of functions that are defined by 2-layer perceptron, right? They're parameterized by basically by the weights and biases of these 2 layers, is dense in the class of continuous d-dimensional functions. Okay, so dense means that it's basically I can be epsilon close to any of these functions, and basically this is called one of the universal approximation theorems. Again, I don't want to prove it, so you can find the proofs online, but the way to see it is that with this simple configuration of neurons, I can represent a step function, right? So if I can represent a step function, I can approximate any continuous function as a sequence of steps, right? So this result, this is the formal statement of this result. It assumes fixed number of layers, right? So this is bounded depth, but it has arbitrary width, right? So it doesn't tell you how many neurons you need. It also doesn't tell you how to find their parameters, right? So it's an existence result. It's not really a solution of the problem. And there are stronger results, so you can bound both the depth and the width. And again, that's why it's not a single result, it's a class of results. Okay? But the question that we are interested in is what is the relation between the dimensionality, the number of neurons, and the error? Okay? And here it really depends on the class of functions. So basically we want a bound on the approximation error for different classes of functions. So they take mathematicians' favorite class of functions, right? So when people in approximation theory talk about regularity, probably the first thing that comes is the Sobolev class. So these are basically this is the class of functions with bounded Fourier transforms, right? So where the moments decay fast, right? So these functions behave nicely, right? So in this case, the error is exponential, right? It's exponential in the dimension, so it's dimensionality cursed, right? So these are functions with, you can think of them functions with sufficiently many derivatives, and this is too big a class, right? So it's dimensionality cursed. You can think of other classes, right? So people design special classes of functions that are well behaved, right? So they're not dimensionality cursed, but these classes are too narrow, right? They're not interesting. Is there some issue? Is there some issue, or?
Yeah, okay. You want to use mic?
No, I'm fine. Yeah. So how are we doing with time? When do we need to make the break? Okay. Yeah, so basically this is called the Baron class, right, after its inventor, and you can see that this assumption is too strong in practice. So it's not dimensionality cursed, right, but this class of functions is not very interesting, right? Now, the last source of errors is optimization, and here actually the situation is more optimistic, right? When we talk about optimization, right, so typically this is how what we are interested in, right? So we want to find the global optimum of some high-dimensional function, right? So this is how our loss function looks like. It is typically non-convex, right? So finding this minimum is an intractable problem, right? So we are interested in this, right? In practice, we can find a local minimum, right? Of course, not every minimum is the same. So this is a good minimum, right? Because it's close to the global minimum, and this is a bad minimum because it's far from the global minimum, right? So this is unfortunate situation, right? So this is how machine learning problems look like, but the reality looks more benign. So the reality looks like more like this. So there are many local minima, but most of them are good minima, right? So it doesn't matter if I find this one or this one. They are roughly all the same, right? And basically most local minima will yield similar performance, and therefore you don't even need to optimize to to find exactly the minimizer of your loss function, right? Because they're after all the same. And here's an example. So this is already 10 years old paper by Koromanska. So here you can see the distribution of losses, right? So it's basically it's histograms of neural networks of different depths. And you can see when the networks are shallow, then the variance is very large, right? So you can get very large losses and you can get very small losses, right? So it looks more like this, right? So you have very low minima and you have very high minima. But as you make the neural networks deeper, right? So when, for example, the red one is 500 layers, you will see that the distribution of loss values will become much sharper, and it has to do with the fact that the loss landscape looks more or less like this, right? So all the local minima look more or less the same. So that, again, there's some statistical explanations why this is the case, but bottom line is that this is not a problem, right? What you can also show, again, there's plenty of literature in optimization. You can actually find efficiently local minima of, especially when you use stochastic gradients, right? That's what people use to optimize deep neural networks. So there is no issue with optimization, right? So even though at surface it looks like a difficult and intractable problem, in practice it does work, right? So this is what we need to know. Okay, so this brings us to the topic of geometric regularity, and this will be basically the topic of the further investigation. So basically, let's just summarize the findings so far, right? So remember, we had these two errors. We had the approximation error and the estimation error, and we looked at one class of functions, like Lipschitz functions. So in a sense, Lipschitz class is too large, right? So its estimation error is dimensionality cursed, right? So this one, right? Remember? So we had this example, right? Why Lipschitz functions are problematic. We looked at another class of functions, the Sobolev class, right? So the Sobolev class, on the other hand, is too small, right? So in this case, the approximation error is dimensionality cursed, right? So again, we have a trade-off between the two. So one is too large, another one is too small. So we need some other notion of regularity that somehow will be able to address the curse of dimensionality and not be too restrictive. So we want some kind of functions that still make sense, right, in our problems, but can offer us salvation from the curse of dimensionality. And these are geometric priors. Basically, we'll be coming from the assumption that our data is not just a d-dimensional vector. It's actually data that lives on some geometric space, right? So when we talk about images, these are functions on a grid, right? And the grid, we can associate some class of transformations, what we will call a group, right? So we can act on the grid and on signals that live on the grid with some group, right? And from this we'll derive a new notion of regularity, and this will be basically our mathematical foundation for the discussion of geometric architectures. And when I say geometric, basically more or less anything. Convolutional neural networks, graph neural networks, they will all come from the same principles, right? So basically, what you need to take away from this discussion is the notion of the curse of dimensionality, right? So basically, it is there in the machine learning problems. So you cannot solve these problems without making some prior assumptions, right? So even if you think that your neural network doesn't have a prior, there is a prior, right? So at least some continuity, right? So this is what the prior in, for example, in perceptrons. And the classical notions of regularity, right? So what people use in approximation theory are not good enough. So they're too weak or too or dimensionality cursed. So we need, and this will what we'll be discussing in the next lecture is geometric priors, right? So how to use group theory to come up with new notions of regularity. Okay, I will stop here. Any questions so far? Is it clear or unclear? Yeah, I think it raised a question there.
So, Professor Bronstein, so I would like to thank you, and I appreciate your time coming here and teaching our students. It's such an opportunity for them. I basically don't have question, but it just reminded me 15 years ago in the classes when we were learning about fundamental of machine learning and optimization. It just went over my head. So I just wanted to tell all of the students, you might understand everything here, or many might be confused. So it's normal. And as time goes by, you will understand. So thank you again for it.
Thank you. Well, I don't expect that you get everything immediately, but at least if something sticks, right? So at least some take-home messages, then it's probably still good enough, right?
Good morning, sir. I wanted to ask that double descent that you mentioned in the modern region. What made? I mean, how are they ensuring the double descent? Or what sort of architectures or losses or things like that are causing the second descent?
So what causes the second descent is the fact that you have way more parameters. So neural network, right? So if you think of modern neural networks, so they have billions of parameters. So they can learn, they can memorize the training set, right? So that's when we say interpolation, it's exactly this, right? So I can fit exactly the training set, right? So, but if you continue increasing the complexity of the model, you will get better generalization, right? So that's basically, this was one of the reasons why deep neural networks work well, right? So that you can go beyond the interpolation and you get better generalization.
And
so the losses are the same losses that you use classification loss or regression loss, so it's all the same.
So hardware got better, so we got better results. Simply that.
Yeah. So you are beyond the interpolation point.
Thank you.
Good morning, sir. I wanted to understand when you said that the class was too small and it was still caused by dimensionality, the so-called class. What I didn't understand was how does increasing the data points help us find a better solution if the class is too small to find a good estimator for this problem?
So it has nothing to do with the training set size, right? So the training set size only will affect the estimation error. So here is basically, again, so we are talking about spaces that are infinite, right? So when you say small, of course, it's in the sense that basically how far you are from your ideal function, right? So basically how rich is the class of functions that you're trying to express, right? So small is not, basically it's not a countable, set, of course.
So we are saying that by increasing the dimensions, we do not get a better estimate, or what?
So here dimensionality is fixed.
Okay.
So what you change is what kind of functions you are looking at, right?
Okay.
So you need to make some assumptions about the functions. So the very basic one is continuous, right? But of course, continuous is too broad. So Lipschitz continuous is slightly more restrictive, but even that is too large, right? But Sobolev, right? So which is basically bounding the moments of the Fourier transform, which basically saying that this function has sufficiently many derivatives is too restrictive, right? So basically you get the cursed by dimensionality in another place, right? Whether in approximation or in estimation.
Hello, good morning everyone. So I want to ask the question, what does it mean that when the estimation error and approximation error are same, does this mean that the model perfectly fits for the training sets of data?
You mean that both errors are 0?
No, it can be same with some constant values.
I mean, you mean that the two curves cross? Nothing to, I mean, probably nothing, I don't know. No particular interpretation that I'm aware of.
Does that mean that the model perfectly fits for the training set of data? Means that underfitting or overfitting is not that like?
So if you look at the gain, so let's, maybe I'm missing the question. Sorry, let me, just a second. So where is, yeah, so this is the curve. So, well, so underfitting means this, right? So you have, so basically your error is composed of two parts, right? So the estimation and the approximation. So when the model complexity is higher, so you're asking about this question when the two two things cross. I don't necessarily see, so and you're asking whether it corresponds to some kind of optimal minimum here. I don't think so. So it really depends on how specifically this curve looks like. I wouldn't attribute any particular meaning to it, but I might be wrong. Yeah, I don't know.
Thank you, Professor.
Yep.
Thank you, Professor. So I have two questions. So firstly is just like following up on the double descent. I'm curious whether double descent it's more of an empirical observation, or is there a theoretical explanation for why that happens? And the second question is, you also mentioned that most local minimums give the same result, right? And I suppose that that result is based on experiments on a multi-layer perceptron. But like, do you think that would change for more complicated architectures like transformers and other architectures?
Yeah, I think it's general. So it's the behavior of the. Of course, it depends on the neural network architecture. But I think the plot that I showed were actually for convolutional neural networks. So I think it's observed across the board. Of course, it depends on the data. It depends on the problem. But in most cases, this is what happens.
On the double descent.
On the double descent, yeah. So there are some attempts to understand theoretically why it happens, but again, the main argument, at least that Belkin shows, is that basically when you go beyond the interpolation point.
So it's more empirical observation.
Empirical plus some attempt to explain it. Yeah.
Hello, sir. My name is Amber. I am working in Area of Biometrics. So first of all, it's a great, thanks a lot to have. It's great to have your lecture in person for the very first time. And my question is basically on quantization. When we do quantization, it leads to the loss of information. So how can we prove that not enough information has been lost and our results are accurate? How can we prove this thing? This came across multiple times in my.
So when you say quantization, you mean of the neural network itself, right?
Basically, I'm talking about data points, minutia points to fingerprints. Basically, you can take any coordinates, let's say, are there in the space, and we are quantizing to a particular data set. Let's say vector, one-dimensional vector. So there is always a loss of information. So how to prove that it's not there?
Well, so quantization, so again, if I understand correctly the question, so basically when you, for example, you use finite precision arithmetics, right? So what people often use with, to basically to make the neural networks more efficient. So usually it's treated as noise. So it's a special type of noise. Sometimes it can be considered as a feature rather than a bug, because it can make your architecture more robust. So yeah. Otherwise, I don't know what to say about it.
How we have to prove that whatever we have got results are perfectly accurate in this regard.
I'm not sure I'm following the question, but we can.
Discuss with you offline.
Yeah, of course.
Thank you.
Hello. So you said that when we increase the domain, estimation error increases, and on decreasing the domain, the approximation error increases. In between these, we find the optimization value. So how could we guarantee that the optimization that we found out between the estimation and approximation error is the global optimum? Yeah,
so the argument that I showed is that we usually we cannot guarantee that this is a global optimum, but usually the optimization error is small, right? So when the network is sufficiently deep, right, and you don't get a big difference between the local and the global minimum. So basically, you can disregard the optimization error. First of all, you can never find the true global optimum, but it's not even necessary. All the local optima are roughly the same, right? So that's why optimization error is usually not even considered.
So what's the case if the perceptron layer is small? You said that when the layers of the neural network is small, the difference is large. So what's the matter in that case?
So when the neural network is small, you will have a low capacity, so it's you will probably be in the underfitting region. So when basically your hypothesis class is not rich enough to fit the data. So underfitting, basically.
Thank you.
Good morning, sir. So my question may be an extension to this lecture you gave. So like you finished off with groups. So we know that there are two popular groups, SO3 and SE3. So we enforce this group transformation using equivariant architecture. So is equivariant architecture necessary, or can it be learned using augmentations? Like, what is your opinion on that?
Yeah, good question. So it's so you can use both, right? So you can learn some groups. So the bigger the group, right, or the higher dimensional it is, the more difficult it is. So I mean, I will talk about it probably in the last lecture. There are not only algorithmic considerations, there is also hardware considerations. So what is called the hardware lottery. So it's easier to implement a plain architecture that is not equivariant, and then if you can basically learn the equivariance from the data with data augmentation. So this is what. So if you take CNNs, right? So translations are not the kind of transformations you are interested in computer vision. So it's a way bigger class of transformations, not even a group, right? So it's bigger than a group. Why? What is so special about translations? Because DSPs, right, and later GPUs very naturally map to these to these kind of architectures, right? The only thing that they can do efficiently is multiply and accumulate, right? So SIMD type, single instruction multiple data type of architecture. So basically everything that is not translations, you learn by data augmentation. So AlexNet, for example, was doing pretty sophisticated data augmentation for images. So think of AlphaFold as well, right? So AlphaFold 3 got rid of all the rotational equivariance in favor of plane transformer, and they do, I think, 50 different rotations or something like this with data augmentation. So it's approximately equivariant, right? So you learn the group. I would say that it's easier to learn a low-dimensional group like SE3. It's difficult to learn something bigger. And when we talk about, for example, equivariance in the space of parameters, so it can be significantly higher dimensions. So this is something that is more difficult to learn. But again, I will talk about it tomorrow.
So another thing is like it is told that equivariant architectures don't scale well. Is that correct or like?
Well, it's probably to a large extent it's correct. So scale in the sense that it's more difficult to implement them, and it's yeah. So if you think of transformers, right? So transformers are a special type of graph neural networks. So there is nothing mathematically special about transformers. They also inherit, for example, permutation symmetry of graph neural networks. So you need to actually break this symmetry with positional encoding if you work on applications that do not require permutation symmetry, like most problems in natural language processing. So why transformers are so popular? Because you can implement them efficiently on the GPU. Right. So again, hardware is the main consideration for the success of this architecture. Yep.
In the slide about model class, there is mention of Sobolev norm. Sobolev, can you please explain in intuitive way what a Sobolev norm is?
Yeah, so the Sobolev space, right, or this class of functions. Well, I have the definition somewhere, but basically these are functions where the moments of the Fourier transform are bounded, And this means that the derivatives exist, right? So there is a relation between the moment of Fourier transform and derivative of higher order of the function. So it means that the function basically is sufficiently smooth, right? So when you have bounded derivatives, it means that basically it doesn't behave crazily, right? Because derivative tells you how the function changes locally, right? So when you take it of derivative of higher order, so it means that it's not completely crazily changing, right? So it's an extension of the standard Lebesgue integrable functions.
Thank you. That was for current Q&A sessions. We can continue the Q&A sessions with the speakers in the debrief itself.
Good. Thank you. So do we have a short break now, right?